Welcome to Math 31. This is a lesson on the product rule. So up till now, we've learned the basic differentiation methods and some of the uses of them, basic applications. Now we're going to raise the bar a little bit and start looking at some of the rules that help us to simplify more complex expressions. First of these being the product rule. You'll end up using the product rule an awful lot in the next few months. So just to illustrate how this whole thing works and some of the false thinking surrounding product rule, let's take a look at two functions, f at x and g at x. Now, when you look at these two, if you were to take the derivative of each one separately, so f prime at x is equal to 2x, and then g prime at x is equal to 3x squared. And then, if you were to multiply them together, so f prime at x times g prime at x, you would get 6x to the 3. So what I did, I differentiated each factor first, or each polynomial first, then multiplied them together. Now let's compare that to what happens if we took, instead, we multiplied the two together. So if we went fg at x, so multiply together first, that would be x to the 2 times x to the 3, which is x to the 5. Add the exponents. So that is fg at x. Now, if we differentiated, we would get fg prime at x, and we would get 5x to the 4. So what this implies, or does more than imply, shows us clearly that the derivative of the product does not equal what we would get when we multiplied the derivatives together. So it does not equal f prime at x times g prime at x. So in other words, it matters. It makes a difference whether you differentiate first then multiply, or whether you multiply first and then differentiate. Question, of course, is which one is correct. You poll people, you might get about a 50-50 split. But in fact, the correct method is the second method that I did. So you need to, if you have two polynomials or two functions, if you didn't know anything else, you could always multiply them together first and then differentiate, and you'd get the right answer. So in other words, this is the correct answer. Now that's not going to be easy for every function, so we have to develop a rule for it. And that leads us to the product rule. The product rule, which I will prove very soon, means, or is stated like this: if y, for any function y is equal to f times g, so two functions being multiplied together, the derivative of those two functions is equal to f prime times g plus f times g prime. Just looking, had to slow down there for a second. Now this means that we take the derivative of the first, that's f prime, leave the second alone, we add it to the first, undifferentiated, multiplied by the second, that it has been differentiated. Now I'm going to show you three ways to write that to further confuse things. If you use Leibniz notation, we would get this. So the derivative d dx of some function uv, so the product of u times v, would be equal to the derivative d dx of the u function times v plus the u function times dv dx. It means that you have to take turns. However many terms you have to differentiate one, leave the others, and then go to the next one. and take the derivative of the second and leave the other ones. Now the better way to write it, the way that I like the best of all, is given y is equal to uv, y prime is equal to u prime times v plus u times v prime. So that illustrates it fairly clearly, I think. So when I use the product rule, I'll usually break it down like this. Some of you will be quicker at it than that, and you'll get good at it, but I would recommend a conservative approach at the beginning. Now the other thing is, if you have three terms, if y is equal to u, v, w, y prime is equal to u prime v, w plus u, v prime, w plus u, v, w prime. So you see how it goes. You take the derivative of one, leave the others. So let's do an example or two. Let's prove it, and then let's do an example or two. Now this is one of the nastier proofs that you're going to see for the next little while. And it would start off like this. So if you wanted to prove this one, if we began with this statement, let's take a function f of x and make this function f of x equal to the product of two other functions. And I'll use p at x times q at x. Letters don't matter, which you choose for these, of course. Now we know, based on the definition of the derivative, that the derivative of f at x, f prime at x, is equal to the limit as h approaches 0 of f at x plus h minus f at x all divided by h. That's how it always goes. Now given that we have this relationship, f at x is actually equal to the product of those two, this statement will make sense, I think. Other than why you'd want to do this. We replace f at x with what it's equal to in terms of p at x and q at x. So therefore, f at x plus h is going to be p at x plus h times q at x plus h. And then the f at x would be p at x, q at x. And then all over top of h. Now this obviously is making things a little bit more complicated temporarily. Now the proof of the product rule is not something that you memorize because, or that you look at and think, I could do that, that would occur to me, because it doesn't work that way. The product rule proof, somebody came up with this, and it's a fairly creative, imaginative proof. So you have to, be humble a little bit when you see it being done. You want it to make sense, but you don't want to feel lousy because you didn't come up with it yourself. Because this next step will not occur to most people. What they did, offhand, I don't know who actually came up with this proof. It might have been Newton and Leibniz themselves. I'm not sure. They did the old add and subtract trick. So out of the blue, they introduced the subtraction of this term, minus p at x, qx plus h. And then, to balance that, they added it on. Now the net effect of that is nothing. You added something and then you subtracted. And you inserted it in the middle of those two original terms. All over h. Then, it occurred to these guys that if they grouped these two together, you could break this into two expressions. So, give myself a little bit more space. I'm going to have to bring up a new screen here, obviously, very quickly. So this would mean the limit as h approaches 0. And take a look at those two terms. First off, the first grouping of 2, you'll see that you have a common factor of q, x plus h. So I'm going to factor out that q, x plus h from those first 2 terms. And that will leave me with p at x plus h minus p at x. And all this is going to be over top of h. So that's the first grouping. And then if you take a look at the second grouping, you'll see that you have a common factor of p at x for both of them. And that's why they chose that particular factor. So that will come out. So we can splitting this into 2 fractions. The p at x is removed from the second grouping, leaving you with q at x plus h minus q at x, and also over h. So it's split up into 2 fractions. And then we now take the limit. So taking the limit would essentially mean that we replace h with 0 if we can. Now we're going to run into a problem though, because of course we have that 0 on the bottom. But if you take a look at first off this first little grouping, p at x plus h minus p at x over h, note that that is actually equal to p prime at x. Just like q at x plus h minus q at x over h for the second grouping is q prime at x. So when we take the limit, in fact, we don't substitute it in, we just change it into another form, the derivative. So I'm going to bring up a new screen just to finish this one off. So when we do take the limit, so I'll repeat that observation, q at x plus h is going to turn into q at x, because the h would be replaced with 0. And then that second factor becomes p prime at x. And then the next grouping, p at x, there's nothing to replace with, so p at x stays as it is, and then q prime at x. So in fact, f prime at x is equal to this. And that's exactly what we saw earlier, where we have the one factor stays as is, the second one we take the derivative of, and we add that to the opposite. So we know it works. This product rule we can use with full confidence now. So let's have a look at a few questions. Let's go through some. Differentiate the following. Number 1, y is equal to 3x squared multiplied by 2x plus 1. Now I know you're thinking out there, I would normally just distribute that 3x squared in and then differentiate. And if you did that, you were in good shape. It's a great way to do it. I'm not going to do it just for the sake of the question. And I'm going to show you the way I usually write this, the way I usually do this. I make substitutions, and I like to work it out in terms of u and v. So u times v. This takes the thinking out of the operation. So u is equal to 3x squared, v is equal to 2x plus 1. And so then I just write u prime. I take the derivative of each one. So this is where this type of notation is useful. The simple prime notation is good for substitutions like this because it's clean and it's very compact. So u prime is equal to 6x. V prime is equal to 2. And since we know that y prime is equal to u prime v plus u v prime, we now just make our substitutions. Y prime is equal to 6x times v, times 2, plus u, which is 3x squared, times v prime, which should be indicated as such, times 2. So y prime is equal to 12x plus 6x squared. Now you can leave it like that, but I'm going to go back and write it in Leibniz notation, which gives us more information. So that prime notation I used just to sort of get me through. There we go. course, you're noticing that I've made a mistake here. This should be u prime times v. So let's pretend this whole incident never happened. Y prime would be equal, let's try it again and get it right this time. So 6x times v, which is 2x plus 1. There we go. So I just did that so you know what not to do. And then 3x squared times v prime, which is 2. Okay, so y prime is then equal to 12x squared plus 6x plus 6x squared. And then y prime is equal to 18x squared plus 6x. So dy dx is equal to 18x squared plus 6x. So there you have it. Now, let's try a few other ones. Number 2. Now this works the same way. You'll get bored with these polynomial ones very quickly. You could have foiled it together, but I'll go through it in this method again, at least try one more. 3x squared minus 1. So u prime is equal to 6x. And then v is equal to x cubed plus 8. So v prime is equal to 3x squared. And as you know, y prime is equal to u prime v, or you will know soon, plus u v prime. So y prime is equal to u prime, which is 6x, times v, which is x cubed plus 8, plus u, which is 3x squared minus 1, times v prime, which I'll write in the front, so 3x squared. So y prime is equal to 6x to the 4 plus 48x plus 3 times 3 is 9x to the 4 minus 3x squared. So y prime is equal to 15x to the 4 minus 3x squared plus 48x. So dy dx could be written in that form. So I'll put it back in Leibniz. 15x to the 4 minus 3x squared plus 48x. Now this somewhat illustrates another point with these, which is that you have to get in the habit of combining like terms and always looking for like terms, because the issue of simplification always comes up. Like, how far should I simplify? How much do I have to do? And the answer to that question is, if there are like terms, you need to get them together. Not always possible or easy to tell, but that's the rule. If there's like terms, you simplify, so that means foiling and gathering them, foiling out polynomials or distributing. And if there are no like terms, then it doesn't matter. Now, number 3, let's do a couple more. No different than anything else, except for the fact that we have these ones in radical form. So u is equal to x to the 2/3. V is equal to x squared plus 5x. So the point with this, if there is a point, is that we have to, as you know, put them in exponential form before you get too carried away with them. U prime then is equal to 2/3. X subtract 1 will give you negative 1/3. And then v prime is equal to 2x plus 5. And as we know, y prime is equal to u prime v plus u v prime. So y prime is equal to u prime, which is 2/3 x to the negative 1/3 times v, which is x squared plus 5x, plus u, which is x to the 2/3, multiplied by v prime, which is 2x plus 5. Now, it's not looking too good. However, we have to distribute those terms in with care, because there is a chance that there will be like terms together. So we multiply the 2/3 x to the negative 1/3 times x to the 2, and we will get 2/3 x. Now when you add the exponents, negative 1/3 plus, just take this to the side, x to the negative 1/3 times x squared is x to the 6/3. And when you add that together, the exponents together, you'll get x to the 5/3. So you have to be careful. And then the next term is plus 2/3 times 5 is 10/3. And then we do the same thing. X to the negative 1/3 times just plain x to the 1, which is 3/3. So add away and we'll get 2/3. And then the next one would be plus 2x. So 2/3 times, or x to the 2/3 times x to the 3/3, add the exponents, you also get 5/3. And then the next would be plus 5x to the 2/3. And we do have like terms now, so we can simplify these. So y prime, we would have to add the 2/3 plus the 2. Now you can use your calculator to add those fractions, or you can get common denominators. 2 is 6/3. So y prime, 2/3 plus 6/3 is 8/3, x to the 5/3. And then for the 2/3 term, this would be denominator of 3 would be 15/3. So 10/3 plus 15/3 is 25/3. And then that's x to the 2/3. So therefore, the derivative dy dx is equal to simply that. And if I made a mistake, which is very easy to do on these ones, when you're talking particularly, somebody will just have to give me a call. But I should be okay. So that's how you tackle these. Again, distribution, simplifying first might have been the easier way to go. But this is really just to illustrate the method more than anything else. There is, I think we can do one more, and as always, pause me at any time if you want to work this one out on your own and compare. I'll go through this, and I'll leave the next ones for another lesson. U is equal to x squared plus 5x plus 1. So u prime is equal to 2x plus 5. And then v is equal to x squared minus 7x plus 3. V prime is equal to 2x minus 7. So y prime is equal to u prime v plus u v prime. So y prime is equal to 2x plus 5 multiplied by v, which is x squared minus 7x plus 3. And unfortunately, we have to now add that to u, which is x squared plus 5x plus 1 times v prime, which is 2x minus 7. And you're probably feeling the same way I am right now. I don't like foiling or distributing binomials into trinomials more than anybody else, but that's what we're going to have to do. There will undoubtedly be like terms with this one. And interestingly, when we get into more complicated ones, they tend to have simplification patterns we can use that help us with it. Whereas these, it's just straight old Armstrong simplification. So y prime, 2x times x squared is 2x to the 3. And then 2x times 7x is minus 14x squared. And then plus 6x. Distribute the 5 in. And we get plus 5x squared minus 35x plus 15. And then we keep on going. We distribute this in. Normally I like to put the binomial in front, but I didn't, and I won't change it now. So this becomes 2x to the 3 minus 7x squared. And then run the 5x through to both. And that becomes plus 10x squared minus 35x. And then the last two terms will be plus 1 times 2x is plus 2x minus 7. And then we just get all those like terms together. So y prime, we have 2x cubed plus 2x cubed is equal to 4x cubed minus 14x squared plus 5x squared minus 7x squared plus 10x squared will give us minus 14 plus 5 is minus 9. Minus 9 minus 7 is minus 16. Minus 16 plus 10 is minus 6x squared. Then plus 6x minus 35x minus 35x plus 2x. So 6x, actually the minus 35 is minus 7t, minus 70x plus 6 is minus 64x, and then minus 64 plus 2 is minus 62x, and then plus 15 minus 7. So 15 minus 7 is plus 8. So that's what our derivative is. Messy business. But I don't know, in this case, would it have been any easier to FOIL it out, to distribute those two trinomials together? Perhaps. And the choice would always be yours. So I'm going to stop it right there. The next lesson we'll pick up and do the remaining examples on your notes, and which don't break a lot of new ground, just show us some variations of these things. And then, so that'll be it for me now. So thank you for your time.